Hello everyone. So in this video I am going to cover fluid properties. So fluid properties में जो भी short notes के form में मैंने इस video को बनाया था. So these short notes will be more than sufficient for your AE/AW examinations. So I will cover all the important points as for the examination point of view. Okay. Let's see. First one is fluid properties. तो पहले यहाँ पर different matters. So whatever may be the matter that is existing is in three forms like solid phase, liquid phase और gaseous phase. यहाँ पर fluids को liquids plus gaseous phase इस दोनों की फेस में जो भी मैटर एग्जिस्ट करेगा उसको हम फ्लूइड कंसिडर करेंगे. ओके. सो आउट ऑफ द थ्री फेजेस ऑफ मैटर सॉलिड लिक्विड एंड गैसेस फ्लूइड्स both liquids and gases comes under fluids. Okay. तो यहाँ पर क्वेश्चन क्या पूछेगा, which of the following matter comes under fluids? So liquids and gases. ठीक है. तो हम बाद में I will explain you later why both gases and liquid comes under fluids, not solid. Okay. So this part is a fluid dynamics का part है. ठीक है. fluid dynamics का part है. What is the fluid dynamics? Fluid dynamics में हमको we will consider the force that is responsible for the fluid. Okay. We consider the forces. I mean to say let's say some liquid is flowing. So अगर liquid flow करने का मतलब क्या है कि उसके ऊपर कुछ forces लगेगा. तो in case of fluid dynamics we consider the forces that are responsible for the flow and we consider these forces in the analysis of the flow. In the analysis of the flow we consider these forces in case of fluid dynamics. In case of fluid kinetics, we don't consider the forces that are responsible for the flow. We analyze the fluid flow, but without considering the forces that are responsible for the flow. So in case of fluid dynamics, there are different kind of forces that are acting on the flowing fluid. First one is pressure force, second one is gravity force, third one is viscous force, fourth one is compressibility force, fifth one is turbulent force, and final one is due to surface tension, the force due to surface tension. If we consider all these forces in the analysis of the fluid flow, if we consider all these forces, then that equation of motion we take it as Newton's equation of motion. We name it as Newton's equation of motion. Okay. So we consider all the forces that are responsible for the fluid flow, and if we consider all these forces into analysis of the flow, then we name it as Newton's equation of motion. Okay. तो अगर इस सभी फोर्सों में if we neglect some forces, like if we neglect surface tension and force due to turbulent force, if we neglect both surface tension and turbulent flow, if we neglect all these things and if we consider pressure force, gravity force, viscous force and force due to compressibility, then that equation is known as Reynolds equation of motion. We name it as Reynolds equation of motion. If you see here, pressure force, gravity force, pressure due to viscosity and pressure due to turbulent force. So इन सभी फोर्सों को हम इक्वेशन ऑफ मोशन में कंसिडर करेंगे, देन वी विल नेम इट एज रेनॉल्ड्स इक्वेशन ऑफ मोशन. ओके. इफ वी नेग्लेक्ट the force that is the turbulent force further, then we name it as Navier-Stokes equation. We name it as Navier-Stokes equation of motion. So Navier-Stokes equation of motion में what forces we consider? We consider pressure force, gravity force and force due to viscosity. And if we consider further, if we consider only pressure force and gravity force in the analysis of the fluid flow, then we name it as Euler's equation of motion. We name it as Euler's equation of motion. You get all these things in fluid dynamics. We generally don't discuss in fluid properties. So you get all these things in fluid dynamics. Okay. So fluid dynamics we will discuss. So in case of fluid dynamics, if we consider all the forces in the analysis of the fluid flow, if we consider all the forces that are acting on the flowing fluid, then we name it as Newton's equation of motion. And if we consider only pressure and gravity force, then we name it as Euler's equation of motion. If we consider pressure force, gravity force and viscous force, we name it as Navier-Stokes equation. And if we consider pressure force, gravity force, force due to viscosity and turbulent force, we name it as Reynolds equation of motion. Okay. So the next one is viscosity. In the viscosity we have two terms, one is dynamic viscosity and another one is kinematic viscosity. So for dynamic viscosity these are the SI units. SI units kya hai? Newton second per meter square, and for kinematic viscosity it is meter square per second. And if we consider CGS units, the CGS units for dynamic viscosity is poise, and for kinematic viscosity it is Stokes. Okay, so 1 poise is equals to 0.1 Newton second per meter square, and 1 Stoke is equals to 10 to the power of minus 4 meter square per second. These are these two are CGS units and these are SI units. You should remember this relationship also, relationship between CGS units and SI units of dynamic viscosity and kinematic viscosity. Okay, so first of all, what is fluid? ओके ये सीक्वेंस में नहीं दिया था, पहले हमको फ्लूइड के बारे में पता होना चाहिए. फ्लूइड इज द सब्सटेंस, if you apply any small amount of shear stress on a fluid, then it will keep on deforming. ठीक है, so the fluid we define it as, if we apply any small amount of shear force on it, if you apply any amount of shear force or if you say shear stress, उस shear force और shear stress को वो resist नहीं कर पाएगा fluid. Okay, so and it cannot resistance any amount of shear force, and it continuously deform once you apply any kind of shear force. Okay, so fluid is defined as a substance having ability to flow, or you can say it continuously deform under the action of shear force, however small it may be. It may be any small quantity, but once if we apply any shear stress or shear force, it continuously deforms. Okay, so that is the definition of fluid, and this condition is satisfied by both liquid and gaseous matter. So both liquid and gaseous are considered under fluid. Okay, this statement is satisfied by both liquid and gases. So these two is considered as fluid. Okay, so next further one, so d theta by dt, this is the term we indicated rate of angular deformation or rate of shear strain. So both these terms are same, rate of shear strain or rate of angular deformation is same. So first we know what is the definition of fluid. Fluid is the thing, if you apply any amount of shear stress, it will continuously deform. Okay, it will continuously deform and it cannot resist any small amount of shear stress. After that, what is d theta by dt? D theta by dt is rate of shear strain or rate of angular deformation. Next one. So between any kind of fluid, between the fluid molecules, there exist cohesive forces. Okay, if you consider any two molecules, between them there is a chance of there will be some attractive forces. If you consider any fluid, let's take water. Between water molecule and water molecules, there exists some kind of attractive force between those molecules. That is taken as cohesion. If you consider two different molecules, let's say the glass molecule and water molecule, or glass molecule or mercury molecule, or or water molecule and air molecule, these are two different molecules. So between these two different molecules also there exists some kind of attractive force between those two molecules also. So that force is known as adhesive forces. Okay, so between same molecules, between same kind of molecules, if there is attractive force, then that is known as cohesion. Between two different molecules in the sense two different material molecules, like water and air, water and mercury, water and gas, two different kind of molecules, right? Between those two molecules, if there is attractive force, then that is known as adhesive force. So you should remember what is cohesive forces of attraction and adhesion forces of attraction, right? If the two molecules of same kind, then that is cohesion. If two different kind of molecules, then that is adhesion, right? Next one. Next one. So if you take the fluid at rest for static fluid, what is the shear force? If you consider the static fluid, in case of static fluid, will be no relative motion between different layers of the fluid. If you consider two different layers of fluid, there will be no relative motion between them. Okay, in case of static fluid, there will be no relative motion between the different layers of the fluid. So due to that, there exists no shear stress. That is tau is equals to 0. There exists no shear stress. Okay, so for static fluid, the shear force or shear stress will be 0. The shear force or shear stress will be 0. If you apply any external shear force, what will happen? The fluid may not remain as static. If you apply any small amount of shear force externally, it cannot resist the external shear force. Due to that, it will continuously deform, or you can say it will flow if you apply any small amount of shear force externally. Okay, so this is overall all about what is fluid, and both liquid and gases comes under fluid. Why? It cannot resist any small amount of shear stress, right? So next one is, what are the properties of fluid? Okay, we have defined already what is fluid, and we have to discuss what are the properties of fluid. So first property is density or mass density. Density or mass density, it is nothing but density or mass density is equals to mass per unit volume. Mass per unit volume. So the SI units is nothing but kg per meter cube is the SI units. Mass per unit volume kg per meter cube. So how the density will vary? Okay, the mass will increases in, let's take a unit volume of fluid. If there is more number of molecules in that unit volume, if there is more number of molecules of that fluid, then there will be more weight, or you can say more mass per unit volume. So then there will be more density. Okay, so if you take density is equals to mass by volume. Okay, let's take per unit volume some amount of volume. If you take, if there is more number of molecules, in that volume, then there will be more mass. So as mass is increasing, so density will increase. Okay, so steel has more density compared to cotton, because steel has more number of molecules if you, per unit volume, if it has more number of molecules per unit volume. Okay, so as any material has more number of molecules with respect to some volume or unit volume, that will have more mass. It indicates that will have more density. Okay, steel has more density. Why? It has more number of molecules. It has more number of molecules per unit volume. Okay, or you can say more mass. Further, this point is important. Water will have maximum density at 4 degrees centigrade. Water will have maximum density at 4 degrees centigrade. Below 4 degrees centigrade or above 4 degrees centigrade, it will have lesser density. Okay, so exactly at 4 degrees centigrade, it will have more density. Why? Because if the temperature is below 4 degrees centigrade, the water will frozen. Okay, you know, the density of the ice is less than when compared with density of water. Okay, so why density of ice is more or less when compared to density of water? So below 4 degrees centigrade, you will have less density. If you increase the temperature above 4 degrees centigrade, what will happen? The molecules of the water will have higher energy. Due to that, they move randomly, and because of that, there will be higher gaps between those molecules. So as the molecule as the gap between molecule is increasing, so the density will decrease. As the gaps are increasing, density will decrease. So at exactly 4 degrees centigrade, water will have more density. Okay, so this is important point. Next one is ice. Ice has lesser density when compared with water. Ice has lesser density when compared with water, because ice more volume due to presence of vacant gaps, so density decreases. Why ice has less density? Because it has more gaps. So due to it is having more gaps, the density of the ice is less when compared with water. Okay, and water will have maximum density at 4 degrees centigrade. Okay, next one is seawater has more density when compared with normal water. Seawater has more density when compared with normal water. These are the important points, like bullet points. You should remember all these things. Next one. Next important how this density changes with respect to temperature and pressure. Okay, how this will change with respect to temperature and pressure. If you consider liquid, it does not change. With respect to pressure, it does not change. With respect to pressure, it does not change. Density is constant. If you consider liquid variation with respect to temperature, as you increase the temperature, so the volume of the liquid will increase. That means the density of the liquid will decrease. So temperature is inversely proportional to density in case of liquids. Okay, so here let's see the pressure increasing. As the pressure is increasing, where is the liquid? Okay, here the pressure is increasing, the density of the liquid is constant. It does not change much. Density of the liquid does not change with respect to the pressure. If you consider temperature variation of the liquid, as the temperature of the liquid is increasing, density of the liquid will decrease. Okay, let's see how gases will vary. As you increase the pressure, the volume of the gas will decrease. Why? The gaps between the gaseous molecules will decrease. The gaps decrease हो जाएगा, इसके हिसाब से volume कम हो जाएगा, so density will increase. So as you increase the pressure, density of the gas will increase. First one here you can say pressure is increasing, volume of the gas will decrease, so density will increase. So if volume less, density more. So with respect to pressure, the density of the gas will increase. One derivation. Second one is with respect to temperature, how it will vary. If you consider with respect to pressure, as you increase the pressure, the volume of the gas will increase, so density will decrease. So density of the gas is inversely proportional to temperature. Density of a liquid with respect to pressure is constant. Okay, these are the relationship of density of liquid and gases with respect to pressure and temperature. With respect to pressure, the liquid density does not vary. With respect to temperature, it will decrease. Next one, gases with respect to pressure, the density will increase because the volume of the gas will decrease. So when you apply pressure, the volume of the gas will decrease. So due to that, density increase हो जाएगा. With respect to temperature, as you increase the temperature of the gas, the density of the gas will decrease because the volume of the gas will increase. Okay, these are the few important points you should remember. Okay, so density basically represents number of molecules occupying a particular volume. As we have discussed earlier, for a particular volume, if the number of molecules are more, the mass will be more, density will be more. Okay, so more the number of molecules, more will be the mass, and heavy will be the fluid. As more the number of molecules in that volume, in that particular volume, the mass of the fluid will be more, so due to that, density will be more, though you can name it as heavy fluid. Okay, so next important property is specific weight or weight density. So specific weight or weight density is nothing but weight of the fluid per unit volume. Weight of the fluid per unit volume, we name it as specific weight or weight density. So that is weight of the fluid by volume of the fluid. So how can you write it as weight of the fluid is nothing but mass of the fluid into Z, gravitational constant, divided by V. So m by V is nothing but mass per unit volume. You name it as rho into Z. So specific weight of any fluid will be equals to, let's take it, any fluid will be equals to density of the fluid into gravitational constant. Density of the fluid into gravitational constant. So that is D into G, that is density into G, you name it as rho. W is equals to rho into Z. Okay, that is specific weight or weight density. Okay, you mention it as W, that is rho into G. Okay, so you have to know rho of water is how much. Okay. So here few important things, and the unit will be Newton per meter cube. Weight by volume, so that will be Newton per meter cube. So what will be the specific weight of different fluids? So for water, rho is equals to 1000 kg per meter cube. For water, rho is equals to 1000 kg per meter cube. So specific weight will be 1000 into 9.81, so that will be 9.81 kilonewton per meter cube. It will be 9.81 kilonewton per meter cube. If you take mercury, rho will be 13,600. So W will be 13,600 into 9.81 will be the, it will be in terms of Newton per meter cube. It is in terms of kg per meter cube. You should remember these two fluids density you should remember. That is 1000 kg per meter cube, 13,600 kg per meter cube. Okay, so next point. Next one is specific weight depends upon both pressure. Specific weight, how it will vary with respect to pressure and temperature is not important. Okay, specific weight is a variable quantity and density is absolute quantity. Okay, density, specific weight depends upon the density of the fluid and gravitational constant. So density is absolute quantity and specific weight is a variable quantity. Next important property is specific gravity. We name it as Z or S. Okay, specific gravity is nothing but we define it as rho of the fluid divided by rho of the standard fluid, or you can say specific weight of that fluid divided by specific weight of standard fluid. This is the definition of specific gravity. So specific gravity is equals to density of the fluid divided by density of the standard fluid, or specific weight of the fluid divided by specific weight of standard fluid. Both are same. Okay, so this is the definition of specific gravity. Okay, so this is standard fluid that we are mentioning here, that the standard fluid will be water for in case of liquids. If we consider, if we are defining specific gravity of any liquid, then we take it the standard fluid as water. If we are defining specific gravity of gas, we take standard fluid as air. Okay, this is the important point. Okay, so relative density is not important, you skip it. Next one. Okay, here you can see, so how he is defining specific gravity. Weight of the density, weight density of a fluid divided by weight density of a standard fluid, or you can say density of a fluid divided by density of standard fluid. Both are same, right? Next. Next one is, so density of water is how much? Density of water is 1000 kg per meter cube. In terms of CGS units, if you take, it is nothing but 1 gram per centimeter cube. Mercury, for mercury density is 13.6 gram per centimeter cube. Okay, so you have to remember only these two. Remaining things are not important. Okay, so now we have some basic concepts here. Okay, with respect to density, we have a concept here. For suppose if a fluid has more density with respect to, if a fluid, or you can say if a body has more density when compared with water, it will submerge, or you can say it will sink in water. If the body, or you can say if the fluid has less density with respect to water, it will float. Okay, so if you see, consider mercury has more density when compared with water. So if we add mercury in water, then it will submerge because it has more density, or you can say more specific gravity. More density or more specific gravity. That is, specific gravity is more than 1 is nothing but it has more density when compared with water. Okay, so if petrol is added to water, it will float. Why? It has less density when compared with water. So you can say specific gravity is less than 1. That is, specific gravity is petrol is 0.75, which is less than 1. So if specific gravity is more than 1, then it will submerge in water. Whatever may be the fluid, it will submerge in water. If specific gravity is less than 1, then it will float with respect to water. It will float on the surface of water. Okay, if petrol and diesel are mixed, then petrol will have 0.75, diesel it will be below it. Okay, so specific gravity basically shows which bodies or which fluids will float, which will get completely submerged. Okay, so which body or fluid will float? If that is S is less than 1, that is specific gravity of the fluid or body is less than 1, then it will float. Submerge kab hoga? If the specific gravity of the fluid, or you can say of the body, is greater than 1, then it will submerge. This is basic concept with respect to density, or you mention it with respect to specific gravity. Okay, next వచ్చేసరికి next क्या है viscosity. So it's not in a proper sequence. We have already discussed what is the units of viscosity and how it will vary with respect to all these things. Now we are getting the definition of viscosity. Okay, let's discuss how viscosity we mentioned it with respect to mu. So it is the resistance between two different or you can say two adjacent layer of the fluid. Let's suppose these are the two different adjacent layers of the fluid. If one fluid is moving with respect to other fluid, the bottom layer or adjacent layer will offer some resistance on the second layer, on the top layer. So it is the resistance between two adjacent layer of the fluid. It is resistance between two adjacent layer of the fluid. If the top layer is moving with some velocity u with respect to the bottom layer, then the bottom layer will apply some resistance against its motion. So this property is taken as viscosity. This property is defined as viscosity. Okay, if you consider two solid blocks, let's suppose it has a solid, and if you try to move the solid on the solid block, this surface will apply some shear some force which is known as frictional force. So if two solid blocks are moving with respect to each other, there develops frictional force. That resistance is known as friction. For suppose one fluid is flowing, and suddenly if there is some solid block, or you can say if there is some solid block, this fluid tries to pull this solid block along it. That is known as drag force. And if between two fluid layers, between two fluid adjacent layer, there exists viscosity. It tries to resist the motion of the adjacent layer. That is known as viscosity. Okay, so and these are the two different layers. Let's assume these are the two different layers of the fluid, and it is moving with some velocity u, and it is moving with some velocity u plus du. In t time, it will travel a distance of u into dt, and it will travel a distance of u into dt plus du into dt. Okay, so this excess distance is taken as du into dt, and this gap between these adjacent two layers is taken as dy. Okay, in t time it has moved in this distance. Let's take this is theta, this is d theta. So d theta by dy is equals to du into dt. D theta by dy is equals to du into dt. So d theta by dt is equals to du into dy. This is the important conclusion we get here. So d theta by dt is nothing but rate of angular deformation, or you can say rate of shear strain. So du by dy is nothing but velocity gradient in the direction of y. This is the direction of y. This is direction of y, and this is the direction of motion. This is direction of flow, and perpendicular in the perpendicular direction we are taking it as direction of y. So d theta by dt is nothing but rate of angular deformation or a rate of shear strain, and du by dy we take it as velocity gradient in the direction of y. So both are equal. We are getting this conclusion of both are equal. This is important conclusion. From these conclusions we are calculating the shear stress and all these things. Okay, so next one is so this results clearly shows what results, that d theta by dt is equals to du by dy. This results clearly shows velocity gradient is nothing but rate of angular deformations. That is the velocity gradient du by dy is nothing but rate of angular deformation, that is d theta by dt, because both are due to molecular bonding and molecular cohesive bonding. Okay, from this conclusion we will get Newton's law of viscosity. If you take Newton's law of viscosity, what it indicates, it states that in a flowing fluid, the shear stress that develops is directly proportional to angular deformation. It is angular deformation, or you can say rate of angular deformation, d theta by dt. So what d theta by dt is nothing but du by dy. Okay, let's see here. The shear stress that develops is directly proportional to rate of shear strain, that is d theta by dt, R. Velocity gradient, that is du by dy. Rate of shear strain is nothing but d theta by dt. This is Newton's law of viscosity. The fluid which obeys Newton's law of viscosity is taken as Newtonian fluid. Is mentioned, we name it as Newtonian fluid. So what this Newton's law of viscosity states, that is the shear stress is directly proportional to d theta by dt, that is the rate of angular deformation, or du by dy, that is velocity gradient. Okay, so this proportionality constant, that is we name it as mu into d theta by dt, or that is mu into du by dy. So this, in this case, this mu is, we name it as dynamic viscosity or viscosity. In few questions they are mentioning only viscosity. If he only mentions viscosity, then you should take it as dynamic viscosity. Okay, by default you should take it as dynamic viscosity. So that mu is nothing but viscosity or dynamic viscosity. That proportionality constant is taken as dynamic viscosity or viscosity. Okay, so what is d theta by dt? D theta by dt is nothing but rate of angular deformation or rate of shear strain, and du by dy is nothing but velocity gradient in the direction of y. So whatever may be the fluid that satisfies this condition, we name it as Newtonian fluid. So for Newtonian fluid, viscosity is constant, which is nothing but dynamic viscosity or viscosity. So for Newtonian fluid, viscosity is constant. Viscosity is constant, and it obeys this condition. Okay. So next one is what are the units of viscosity? Units of viscosity, we have already mentioned it. We have already mentioned is for dynamic viscosity, the SI units are Newton second per meter square, and CGS units are poise. Okay, next one. Next one. So the relationship between CGS and SI units, what did we mention? The relationship is 1 poise is equals to 0.1 Newton second per meter square. We mentioned this relationship already, right? So main reason for viscosity of liquid and gases. In case of liquids, what is the main reason for this viscosity property, and what is the main reason for showing this viscosity property in case of gases? In case of liquids, the main reason for showing the viscosity property is the cohesive attraction forces between the molecules. The cohesive attractive forces between the molecules is main reason for showing this viscosity property. In case of gases, the main reason for showing this viscosity property in case of gases is molecular collisions. Random molecular collisions is the main reasons. Okay, so in case of liquids, it's mainly due to molecular bonding, or you can say cohesive bonding, molecular cohesive bonding. And if you increase the temperature, in case of gases, it is mainly due to molecular collisions or molecular momentum exchange or molecular momentum transfer or molecular collisions. Okay, after that, how this viscosity will vary with respect to temperature. If you increase the temperature, the cohesive forces will weaken. So due to cohesive forces weaken, the viscosity of the liquid will decreases. So the temperature key, with respect to temperature, the viscosity of the liquid is inversely proportional. Okay, in case of gases, what will happen? In case of gases, if you increase the temperatures, the number of molecular collisions will increase. Why? The energy possessed by the gaseous molecule will increase. So due to more energy possessed by these molecules, there will be more number of random collisions. So as there is more number of random collisions, the viscosity of gas will increase. So viscosity of gas is directly proportional to temperature. Okay, temperature. So these are the two important conclusions. Okay, let's see here. So temperature effect, as temperature increasing, dynamic viscosity or viscosity of the liquid will decrease. So this is the relation, and as the temperature is increasing, dynamic viscosity of the gas will increases. Okay, so after that, what is kinematic viscosity? Kinematic viscosity, we define it as, so kinematic viscosity is defined as dynamic viscosity divided by density of the fluid. We name it as kinematic viscosity, And for kinematic viscosity, the SI units are meter square per second and CGS units are Stoke. So 1 Stoke is 10 to the power of minus 4 meter square per second. These are the important point, density, dynamic viscosity by density of the fluid. So, so these are the CGS and SI units relationship for both dynamic viscosity and kinematic viscosity. After that, okay. So effect of temperature on kinematic viscosity, how the temperature will vary. So let's take mu is equals to mu by rho. As you increase the temperature, what will happen? As you increase the temperature in case of liquids, let's take this as a liquid. So mu will decrease with respect to temperature. The density of the the density of the liquid doesn't change much. So let's take it as constant. So overall mu will decreases. Overall mu will decreases. Okay. So with respect to temperature, mu of the liquid will decrease. This is the relationship. Let's take with respect to gases, what will happen? So in case of gases, this is nothing but mu by rho. So if you increase the temperature, it will increase, and the density of the gas will decrease more. So this overall will increase more. This overall it will increase more. So mu of gas is directly proportional to temperature. Mu of gas is directly proportional to temperature. Okay. So this is overall relationships. So these relationships are not important. How it vary with respect to temperature is only important. Whether it is decreases or increases, why it will increase are important. These relationships like to the power of 3 by 2 or square root of temperature, these are not important. Okay. So next one is types of fluid. Next one is types of fluid. How the types of fluid is nothing but practically there are two types of fluids. One is a real fluid, and these two together we name it as real fluids. And second one is ideal fluid. First one is real fluid and second one is ideal fluid. So in case of real fluids, we have subcategory like Newtonian fluid and non-Newtonian fluid. In case of non-Newtonian fluid, there is another subcategory in which there is time dependent fluids and time independent fluids. Okay. So first of all, fluid is divided into two categories. One is real and ideal. And in real fluids, we have Newtonian fluid and non-Newtonian fluid. In non-Newtonian fluid, we have subcategory like time dependent and time independent. Okay. So time dependent and time independent. For time dependent, that is pseudoplastic, dilatant, Bingham plastic. And time independent is thioxotropic and rheopatric. We will discuss all these things in detail in later page. Okay. So first we have to define what is Newtonian fluid. So we have discussed it already. So Newtonian fluid is the fluid which obeys Newton's law of viscosity. That is that the shear stress is directly proportional to velocity gradient or rate of angular deformations. So Newtonian fluids is the fluids which obeys Newton's law of viscosity. Second one, the equation is tau is equals to mu into du by dy. That is the viscosity is constant. So Newtonian fluids will have constant viscosity. If you draw the relationship between tau and du by dy, here it has mentioned here x and y axis are interchanged. We have standard like shear stress on y axis and velocity gradient on x axis. Velocity gradient or angular deformation rate. If you draw the graph, you will have like this linear curve, and the slope of this line is nothing but dynamic viscosity or viscosity. As the slope of this line is constant, so for Newtonian fluids we have constant viscosity. Okay. So all engineering fluids are called Newtonian fluids. Okay. All engineering fluids like water, air, mercury, we name it as Newtonian fluid. Next one, we name it as Newtonian fluid. Next one is non-Newtonian fluid. Non-Newtonian fluid is nothing but which does not obey Newton's law of viscosity. That is, tau is not going to be directly linear relationship with respect to du by dy, d theta by dt. Okay, they do not obey Newton's law of viscosity. their viscosity will change with respect to rate of deformations. Okay, so in case of Newtonian fluid, what did we mention? We mentioned the viscosity of the fluid will be constant, but in case of non-Newtonian fluid, the viscosity will vary with respect to d theta by dt, that is rate of angular deformation, or you can say velocity gradient, or with respect to change. They change with respect to time. Okay, here viscosity mu is not constant. They vary with respect to d theta by dt, that is angular deformation rate, or with respect to time. So the study of non-Newtonian fluids is call it as rheology. In recent UPPSC exam also, UPPSC Uttar Pradesh Public Service Commissioner exam also, they have asked this question. The study of non-Newtonian fluid, we name it as rheology. Okay, so the relationship between tau and du by dy is equals to tau is equals to b plus a into du by dy whole to the power of n. This is the relationship between tau and du by dy for non-Newtonian fluid. This is the relationship for non-Newtonian fluid. So depending upon the b and n value, we will have the relationship between tau and du by dy for different non-Newtonian fluid. Okay, we have a different kind of non-Newtonian fluid, right? So like pseudoplastic, Patrick and thixotropic, we have different non-Newtonian fluids. Depending upon the b value and n value, we get relationship for tau and du by dy for different fluids. Okay, so next one is next page. Okay, so here we have already mentioned it. In case of non-Newtonian fluid, we have subcategory, that is time dependent and time independent. So time independent is nothing but the viscosity will change with respect to time, is independent of time, and here it is time dependent. So first let's discuss time independent fluids. Okay, time independent fluids, if you discuss. So first one is dilatant fluid. If you consider the graph, we have dilatant fluid. For dilatant fluid, how it will vary? This is for Newtonian fluid, and this will be graph. This will be a relationship between tau and d theta by dt, or you can say du by dy. This is the relationship. Okay, this will be the relationship for dilatant fluids. Okay, so if you consider dilatant fluid, here the slope of the curve is increasing. The slope of this curve is increasing with respect to du by dy or d theta by dt. Okay, this is not constant. So mu will vary with respect to du by dy or d theta by dt. क्योंकि वो non-Newtonian fluid है, mu is not constant with respect to d theta by dt. Okay, so here if you see, the relationship will be tau is equals to b will become 0, and du by dy will become a into du by dy whole to the power of n. Here b is equals to 0 and n is greater than 1. B is equals to 0 and n is greater than 1 for dilatant fluid. This is dilatant fluid. Okay, so here we have another term, that is apparent viscosity. We have another term, that is apparent viscosity. Apparent viscosity will be equals to d derivative of tau divided by derivative of du by dy, or you can say it as d tau divided by derivative of d theta by dt. Okay, if you observe properly, this term is nothing but slope of these curves. This slope of these curves is nothing but apparent viscosity. The slope of these curves is nothing but apparent viscosity. Apparent viscosity. So if you consider here, the slope of the curve is increasing with respect to d theta by dt. So you can name it. You can conclude one thing, that is with respect to d theta by dt, the apparent viscosity of this dilatant fluid is increasing. With respect to d theta by dt, the apparent viscosity of the fluid is increasing. So why apparent viscosity is increasing? The slope of the curve is increasing. The slope of the curve is increasing. So here tau is equals to tau naught plus a into du by tau naught is 0. That is this relationship between apparent viscosity. So in case of dilatant fluid, the apparent viscosity will be increasing. The apparent viscosity increases with respect to time. With respect to time. Here it has mentioned here that viscosity will increase with rate of deformation. That is, apparent viscosity will increase with respect to rate of deformation. Why? It is increasing slope curve, right? It is also named as shear thickening fluids. Why shear thickening fluids? The mu value is increasing with respect to deformation rate. With respect to deformation rate, mu is increasing, so we name it as shear thickening fluids. So d theta by dt, as d theta by dt is increasing, the apparent viscosity of the fluid is increasing. Okay, so I have one question for you. The apparent viscosity of the Newtonian fluid, what is the apparent viscosity of the Newtonian fluid? The apparent viscosity of the Newtonian fluid is nothing but dynamic viscosity. Why? The apparent viscosity is nothing but slope of the curve. Here the slope of the curve is nothing but constant, which is mu. So apparent viscosity will be equals to dynamic viscosity for Newtonian fluids. Okay. So in case of non-Newtonian fluid, we have discussed first one is dilatant fluid. For dilatant fluid, the relationship between tau and du by dy will be this curve. As this curve has increasing slope, as the increasing slope, the apparent viscosity of the fluid will increase. Okay. First one is apparent viscosity of the fluid will increase with respect to d theta by dt. We name it as a shear thickening fluid. Why? The density, the apparent viscosity is increasing. Okay. So in case of relationship tau is equals to b plus a into du by dy whole to the power of n, we have b is equals to 0 and n is greater than 1 for dilatant fluid. Okay, so here it has mentioned n is greater than 1 for dilatant fluid. Okay, so examples of dilatant is very important. All the examples for non-Newtonian fluids are very important. So in case of dilatant fluid, the sugar solution, butter solution and corn flour solution are the examples of dilatant fluid. Next one. Next type of curve, that is a pseudoplastic. If you consider the pseudoplastic relationship, if you consider the pseudoplastic relationship with respect to tau on y-axis and d theta by dt or du by dv and y-axis, this is for Newtonian fluid and this will be curve for pseudoplastic. This is the curve for pseudoplastic. If you see, this curve is the slope is decreasing with respect to d theta by dt. So apparent viscosity will decrease. The viscosity will decrease with rate of deformation. With rate of deformation is nothing but d theta by dt. So as with respect to d theta by dt, the tau value is the apparent viscosity is decreasing. So this we name it as a shear thinning fluids. Shear thinning fluids is nothing but mu is decreasing with respect to d theta by dt. So we name it as a shear thinning fluid. So here we have b is equals to 0 and n is less than 1. That is tau is equals to du by dy, a into du by dy whole to the power of n. Here n is less than 1 for pseudoplastic fluids. Okay, so it is also known as a shear thinning fluid. Apparent viscosity will decrease with respect to rate of deformation. Why? Slope is decreasing. Next one is tau is 0 and n is less than 1. Okay, so examples are very important. Blood, milk, ketchup, paints, paper pulp, lipstick, all these examples comes under pseudoplastic. Let's see the complete graph between shear stress and du by dt or d theta by dt. That is rate of deformation, or you can say rate of angular deformation or velocity gradient also on this curve. So this is Newtonian fluid, that is straight line. This is for dilatant fluid, n is greater than 1 and b is equals to 0. And this is for pseudoplastic, that is n is less than 1 and b is equals to 0. And here this is ideal plastic or Bingham plastic fluid, that is b not is equals to 0 but n is equals to 1. And here thixotropic, this is the curve for thixotropic curve. For thixotropic, b not is equals to 0 and n is less than 1. And for rheopatric, b not is equals to 0 and n is greater than 1. These are the non-Newtonian fluids. Next, ideal plastic and Bingham plastic. So this is the curve for ideal plastic or Bingham plastic. I will draw here. This will be the graph for ideal plastic or Bingham. This is a straight line, but it has some initial yield stress, tau naught. You can take it as b. You name it as b. So tau is equals to b plus a into du by dy whole to the power of n. Here b is not is equals to 0 and n is equals to 1. Okay, it will vary linearly with respect to du by dy or d theta by dt. but it has some initial yield stress. Okay, so ideal plastic or Bingham plastic fluids, so it initially behaves as fluids. Why it is initially behaving as fluid? How can you conclude that? Because it can resist initially some initial shear stress. Okay, it can resist initially some shear stress. Even though you have d theta by dt is equals to 0, it has some shear stress. What does it indicate? Even though this is a fluid, it can resist some initial shear stress, or you can say yield stress. So it initially it behaves like a solid after up to some yield stress or initial stress. After that it behaves like a Newtonian fluid. Why? Because n is equals to 1, that is it is varying with respect to du by dy linearly. Okay, so initially it behaves like a solids because it needs some initial, it can resist up to some yield stress or initial shear stress, and after that it will behave like a Newtonian fluid because it is varying linearly with respect to angular deformation rate. So tau is equals to b plus a into du by dy whole to the power of n. In this case b is not is equals to 0 and n is equals to 1 for ideal plastic or Bingham plastic fluid. So what are the example? Drilling mud, Savarage sludge, toothpaste, hair gel, cosmetics, all these examples will comes under ideal plastic or Bingham plastic. Okay, next one is thixotropic and rheopatric. If you consider thixotropic and rheopatric curves, these are the shear thinning fluids. Why? Under this curve, this represents thixotropic and this represents rheopatric. This is this is thixotropic curve. This is thixotropic curve and this represents rheopatric curve. So if you know rheopatric curve, in this case the slope is increasing, so you can say the apparent viscosity is increasing with respect to rate of angular deformation, so you name it as shear thinning fluid. So it is shear thinning fluid. Why? The mu apparent viscosity is increasing with a rate of angular deformation. So this viscosity decreases with time. As time is increasing, it will decrease. With respect to time, it will increase. So this is shear thickening fluid and this is shear thinning fluid. Okay, this is thixotropic and this is rheopatric. Here here this is decreasing. This is, we are talking about thixotropic, that is slope decreasing curve. So the apparent viscosity will decrease. In case of here, the slope is increasing, that is apparent viscosity is increasing, so we name it as a shear thinning fluid. With respect to time, the apparent viscosity will increase, or you can say that viscosity of the fluid will increase. With respect to time, the viscosity of fluid will decreases. So shear thinning fluid, shear thickening fluid. And if you see the relationship, tau is equals to b plus a into du by dy whole to the power of n. For thixotropic fluid, b is not is equals to 0 and n is greater than 1. Sorry, n is less than 1 for this one. If you consider for rheopatric, b is not is equals to 1 and n is greater than 1. Okay, so examples are ice creams, printer ink, yogurt, and for this gypsum paste, bitumen solution. All this comes under rheopatric and these examples comes under thixotropic. Okay, for shear thinning fluid we have two fluids, that is for shear thinning fluid is nothing but mu is decreasing. One is thixotropic and another one is pseudoplastic. And in case of shear thickening fluids, that is with respect to rate of angular deformation, apparent viscosity increasing, those are rheopatric and another one is dilatant. Okay, so this is all about non-Newtonian fluid and Newtonian fluid. That is, we are discussing all these things about real fluids. So next one is ideal fluids. What is the basic definition of ideal fluid? So you know, practically there is no ideal fluid. Okay, practically there is no ideal fluid. We assume it as this is a hypothetical fluid. Okay, practically there is no ideal fluid and we assume it just like that. Okay, it's a hypothetical fluid. So for any ideal fluid, it should satisfy three conditions. Okay, ideal fluid should satisfy three conditions. First one is it should be incompressible. It should be incompressible in the sense, however pressure you apply, whatever may be the pressure under any situation, the density of the fluid should be constant. Okay, it should not vary. You can say incompressible fluid. Second one is it should not have any viscosity. It should not have any property of viscosity. And third one is surface tension should be zero. Sorry, here viscosity should be zero and surface tension should be zero. So these are the examples. Non-viscous is nothing but viscosity should be zero, incompressible is nothing but density should be constant, and negligible surface tension is nothing but surface tension should be zero. So ideal fluid follows the equation of conservation of mass. So equation of conservation of mass is followed by ideal fluid. Okay, these are the important points as per objective point of view. Okay, so next point. And the next property is compressibility. Next property is compressibility. Okay, so what is compressibility first of all? So compressibility means let's take this is the system and we are applying some pressure on this system and we have filled the gas or whatever may be the fluid. Let's take it's a fluid. Okay, if as we are applying pressure, if there is more, what is the volume change? As we are applying some pressure, there will be volume changes in this fluid. Okay, so due to the application of pressure, how much volume is changing? Due to the application of pressure, how much volume is changing? So it relates with compressibility. If you say the fluid is more compressible, that means there will be more volume change due to increase of pressure. Due to increase of pressure, if there is more volume change, then that is called compressible. If there is no much change in volume with respect to due to increase in pressure, then that is called incompressible. Let's take liquid and gas. Let's assume this is gas and this is liquid. In case of liquids, due to application of pressure, there won't be much change in volume. That is, change in volume or decrease in volume is almost zero. And in this case, there will be much significant volume decreasing. The significant volume decrease ho jayega. So due to the application of pressure, if there is more decrease is in volume with respect to pressure, then that is called more compressible. Due to application of pressure, if there is no much change in the volume of the liquid, then that is called incompressible fluid. So liquid is incompressible. Generally we take it as incompressible. For gases, it is compressible. Gases, it is compressible. So next one is, what is the compressibility? Now, first of all, we discussed how what is the compressible and incompressible fluids and its significance in practical way. Now we have to define its definition. What is compressibility? Compressibility is equals to 1 by bulk modulus. 1 by bulk modulus. So bulk modulus is equals to minus of dP divided by dV divided by initial volume. Okay, minus dP divided by dV by V. Here dP is the increase in pressure and dV is the decrease in volume. Okay, V is the initial volume. V is initial volume and dP is increase in pressure, and here is decrease in volume, change in volume or decrease in volume. So what is here minus negative sign क्या indicate करेगा? Negative sign indicate ये करेगा कि due to the increase of pressure, if dP is positive, that means we are increasing the pressure, then volume will decrease, that means dV will be negative क्योंकि volume decrease हो जाएगा due to increase in pressure. So in terms of compressibility लिखेंगे तो the value will be dV divided by dP into initial volume. This will be the compressibility formula. This is bulk modulus formula. The relationship is bulk modulus is compressibility is equals to 1 by bulk modulus, that is 1 by K. Okay, so bulk modulus को क्या define करेंगे? It is a normal stress or direct stress with respect to the volumetric strain. dV divided by V, that is change in volume divided by initial volume, is taken as volumetric strain. So dP is normal stress, or direct stress divided by volumetric strain is taken as bulk modulus. It is taken as bulk modulus, that is this is definition. K is equals to minus dP divided by dV by V. Negative sign indicates that pressure is always compressible. It's not the same way. Negative indicates that due to increase in pressure, volume will decrease. That is, if dP is positive, dV will be negative. So for that we kept my negative sign. Okay. So bulk modulus is mathematically, bulk modulus is equals to minus dP divided by dV by V. This is the mathematical expression for bulk modulus. Okay. The next page. Next one is, next important property is surface tension of fluid. So surface tension is, first of all, it's a property of the liquid surface. It's the property of liquid surface. First of all, surface tension is the property of liquid surface. Goes to, it is the property of liquid surface. Okay. So it's the property of liquid surface. Okay. So क्या होगा, पहले एक मॉलिक्यूल को इनसाइड द लिक्विड कंसिडर करेंगे और एक लिक्विड मॉलिक्यूल को ऑन द सरफेस लिक्विड मॉलिक्यूल को कंसिडर करेंगे. सो लेट अस कंसिडर ए लिक्विड मॉलिक्यूल. हियर इट्स नॉट मॉड्यूल, इट्स मॉलिक्यूल ए. It's molecule A, which is inside the surface of fluid. This molecule is under the action of balanced cohesive forces. Balanced cohesive forces in the sense, if you consider a liquid molecule inside the surface, then this liquid molecule is surrounded by same liquid molecules. This molecule is surrounded by same molecules. So you know, uh, between liquid molecules you have cohesive forces. So due to symmetry on these fluid molecules, the cohesive forces that are applied by the surrounding liquid molecules will be balanced by each other. That means the net force acting on this inside molecule will be zero. Inside molecule will be zero. That is the net force that is acting due to cohesive forces between the molecule will be zero. If you consider the surface molecules, there will be liquid molecules on the sides and below, and it tries to pull the surface molecules downward. So there will be some net downward force is acting, on these surface molecules. So due to that, the surface that is existing will be under tension. It acts like a stretched elastic membrane. Okay. So if we consider molecule on the surface molecule is under the action of unbalanced cohesive forces. Why? Because the water molecule, or you can say the liquid molecule, is only below surface only. Okay. So hence this molecule will experience net downward pull or stretching. So every molecule on the surface will under tension, known as surface tension. So the surface will carry some kind of tensile force, which is due to some net downward forces acting on those molecules, which is known as surface tension. Surface tension is mainly due to what? It is mainly due to unbalanced cohesive force. So in objective point of view, they will ask you, the surface tension is the property attained due to the cohesive forces of molecules. Okay. So mathematically क्या represent करेंगे? Mathematically surface tension is defined as the force acting on an imaginary line drawn on a liquid surface and is acting perpendicular to the line per unit length. I have discussed this surface tension topic in detail in my YouTube channel, so please follow that. Okay. So surface tension is defined as line force. That is, the units of surface tension is force acting per unit length. Okay. So with the increase in temperature, what will happen? With the increase in temperature, the cohesive forces weakens. So due to the cohesive forces are weakened, the surface tension property will decrease. So surface tension is also defined as line. With the increase in temperature, the effect of surface tension will decrease. Why? Due to cohesion forces weakens, right? So warm water is used in washing clothes because the warm water will have less surface tension. Adding detergent and soap solutions, due to adding of detergents and soap solutions, the surface tension of the liquid will decreases. Okay. For ideal fluid, surface tension will be zero. Surface tension at critical point is zero. Why? At critical point, is the pressure and is the temperature and pressure at which the liquid tries to jump into vapor. So at a critical point, the water will experience zero surface tension. Okay. So at a critical point, surface tension will be zero. This is also important point. So due to temperature, how it will change? Due to temperature increase, surface tension of the liquid will decrease. Next point. Next important one is, what is the surface tension of water and air? వాటర్ వచ్చేసరికి at 20 degrees centigrade surface tension of water will be 0.073 Newton per meter. It's not surface tension of water or air, it's the surface tension of water in the interface of air, in the interface of air. Okay, in the interface of air it is 0.073 Newton per meter. You should remember mercury also. For mercury also it's 0.48 Newton per meter. Okay, mercury has higher surface tension when compared with water. Why? It has more cohesive forces. So liquid droplets or soap bubble, it attains spherical shape because it has because due to the property of surface tension. Application of surface tension, we have three kind of applications. One is excess pressure inside liquid droplet. Okay, excess pressure inside liquid droplet, excess pressure calculation inside soap bubble, excess pressure calculation inside liquid jet. So in case of liquid droplet, we have one interface of liquid, with air, so that the external pressure, the excess pressure will be 4 sigma by d in case of liquid droplet. And in case of soap bubble, the surface, or you can say the air and the liquid interface will be 2. So due to that the excess pressure inside soap bubble will be 8 sigma by d. Okay, so after that, pressure inside a liquid jet will be 2 sigma by d. The pressure, excess pressure inside the liquid jet will be 2 sigma by d. These three formulas are important. So this is all about surface tension in brief. So next one is capillarity. So capillarity is nothing but, for suppose if we kept a glass tube, a narrow glass tube inside a liquid, sometimes there is a rise and sometimes there is a fall of liquid inside this glass tube. That is known as capillary action. Okay, when we kept some kind of narrow circular tube inside a liquid, sometimes the liquid surface will rise and sometimes the liquid surface will dip depending upon the liquid that we have kept. That is known as capillary action. So capillary rise occurs when adhesion is greater than cohesion. It is not just due to adhesion. When adhesion is greater than cohesion, capillary fall will occur when cohesion is greater than adhesion. It is not just due to cohesion or adhesion. This is the complete picture. Okay, angle of contact theta. Angle of contact is nothing but, for suppose if a liquid is get in contact with any solid surface, let's suppose this is the solid surface, and if the liquid is get in contact with the solid surface, the angle made by the free surface, tangent to the free surface of the liquid with the solid boundary inside the liquid is taken as angle of contact. Okay, angle of contact is nothing but it is the angle made when a liquid and a solid get in contact. The angle made by the tangent tangent drawn to the liquid surface and solid boundary inside the liquid is taken as inside the liquid. This is the solid boundary. Okay, so this is tangent to the free surface, and this is the angle made by tangent to the free surface and the solid boundary. This is taken as contact angle. So this contact angle will depend upon three things. I mean to say three things. First one is liquid, that is which liquid contact angle we are calculating, and the solid surface, whether it is a glass or some kind of thing, and the third one is interface. Interface in the sense the liquid surface, the free liquid surface is with which one, either it is with gas or air interface. All these three things decides the angle of contact. Okay, so the contact angle depends upon adhesion and cohesion. Okay, so if adhesion is greater than this kind of curvature, that means the theta will be less than, the contact angle will be less than 90 degrees. That is acute when adhesion is greater than cohesion. Adhesion is greater than cohesion in the sense these liquid molecules will try to get in contact with this solid surface because it has more adhesion forces when compared with cohesion. So theta will be less than 90 degrees, that is acute. This contact angle will occur only for the liquids which has more adhesion when compared with cohesion, and it will wet the surface. It will wet the surface. Wetting will occur. If you take some kind of liquid, the example for this kind of liquid is water. Water with glass. Okay. So if you take this kind of glasses, here the cohesive forces is more when compared with adhesion. So the liquid molecules try to get in contact with those molecules only. Okay, it does not want to get in contact with this solid surface molecules. So the contact angle will be it will be greater than 90 degrees and it is less than 180 degrees. That is obtuse angle it will form. So cohesion is greater than adhesion, and non-wetting, it does not wet the surface, or you can say non-wetting case will occur. So for this kind of things, that is if adhesion is greater than cohesion, here capillary rise will occur. Capillary rise will occur, and here capillary fall will occur. Capillary fall will occur. When we have he may ask you in question, when will capillary rise occur? When will capillary rise occur? The capillary rise will occur only when adhesion force is greater when compared with cohesion forces. Okay. So this is all about this value. So what is capillary rise? What is the formula for calculating capillary rise? So capillary rise or capillary fall will be, that is H is equals to 4 sigma cos theta divided by rho GD, or you can say this value. So this can be capillary rise or capillary fall. So capillary fall will occur when cohesion is greater than adhesion, and non-wetting, so that means this liquid does not wet the surface, and angle of contact will be obtuse angle, that is greater than 90 degrees and less than 180 degrees, and value will be 4 sigma cos theta by d. Whether it is a rise or fall, it does not matter, the formula will be same, that is 4 sigma cos theta by rho GD. When rise will occur, when fall will occur, it depends upon the adhesive and cohesive properties, right? After that, next one. So the height of capillary rise or fall is generally seen in glass tube having diameter more than, no, it's not more than 1 meter, it should be less than 1 meter. Kyunki if you know the capillary rise will be equals to 4 sigma cos theta by rho GD. So if you increase the dia of the capillary tube, the height will decrease, capillary rise or capillary fall. So as the dia of the capillary tube is inversely proportional to capillary rise, capillary height, so the dia of the capillary tube should be kept below 1 centimeter to have clear vision of capillary height of capillarity. Okay. The angle of contact in case of capillary rise, where adhesion is greater than compared with cohesion, the angle of contact will be around 22 to 22 degrees centigrade. 22 degrees, not centigrade. So height of capillary fall is occur when cohesion is greater than adhesion. In this case, theta will be greater than 90 degrees, and its angle is generally 128 to 130 degrees. Pure water in contact with glass in the interface of air you should take, angle of contact will be 0 degrees centigrade. Okay. So why meniscus is formed? Because formation of cohesion plus adhesion for surface tension. Okay. So the meniscus is nothing but in case of capillary action. So the liquid molecules will form like this, the surface. The molecule here will attach to the surface of the glass just because it has more cohesive forces when compared with adhesive forces. And after that, the liquid molecules will be in contact with respect to the surrounding liquid molecules due to the surface tension, and they will form meniscus like this. So the meniscus will be formed due to cohesion, adhesion and surface tension. Okay. So this is all about capillary action. So after that, vapor pressure. So vapor pressure is nothing but, for suppose I have a liquid, it is filled with, I have a container, it is filled with liquid. This container is kept at constant temperature. At particular constant temperature, as the liquid molecules have some energy, they tries to vaporize and jump into surrounding air tries to jump into surrounding air. After some particular amount of time, the moisture holding capacity of this surrounding air, that is kept here, the moisture holding capacity of air will be exhausted. That means the moisture holding capacity will be over. So after that, what will happen? The liquid molecules try to jump here, and the same quantity of liquid molecules will jump further from air to liquid. This phase is known as equilibrium phase. This phase is known as equilibrium phase. In this phase, there will be no there will be no net liquid molecules jump into surrounding air. So the surface molecules, due to additional energy, escapes in the form of liquid surface. The air above the liquid surface can absorb water only up to some saturation limit, that is moisture holding capacity. So after saturation is reached, if the surface molecules evaporate in the air, then the same number of molecules will rejoin the liquid surface. This is called phased equilibrium. This is called phased equilibrium is reached. After that, there will be no net molecules exchange. There will be no net molecule exchange between air and liquid. So the vapor inside this air, after attaining this phased equilibrium, they will exert the pressure on the liquid. The force exerted by the vapor on the surface of the liquid is known as vapor pressure. The vapor pressure is a direct function of temperature. Why? If the temperature is increased, the moisture holding capacity of the surrounding air will increase. So due to that, there will be more vapor present in the air. So due to that, the vapor pressure will be more. So vapor pressure is directly proportional to temperature. Okay. So what is the significance of vapor pressure? So vapor pressure, the significance of vapor pressure is cavitation process. So when a liquid, if the absolute vapor pressure at any point in the liquid, absolute vapor pressure is less than P vapor pressure of the fluid, then there is a chance of cavitation occurrence. So cavitation is an undesirable effect. We don't want cavitation to occur. So when the liquid, okay, so this is all about vapor pressure property. So let's take, I have a pipe like this. Some liquid is flowing in the pipe like this. Let's assume there is some Q is flowing. So if you consider here, the pressure is more, here the pressure is less. Why? The velocity is more when compared with, the velocity is more with respect, if you have V1 is here at this section, if V2 is here, so V2 is greater than V1. So due to that, the pressure will be decreasing. So here you will have least pressure. Okay, least pressure. If at this point the pressure, absolute pressure at this section is less than vapor pressure of the fluid, then there will be chances of cavitation occurrence. Cavitation occurrence in the sense, the molecule, here the boiling will take place. Due to this boiling, liquid bubbles will form, air bubbles will form. So once these air bubbles will flow along with the liquid, and when it comes to high pressure zones, what will happen? These air bubbles will collapse. So due to that, what will happen? The surroundings of this area will get damaged. Okay, this is called cavitation, and we don't want this cavitation effect. So for that, we have to maintain some minimum pressure in the flow such that the pressure should not come below vapor pressure. So when the liquid flow through a converging section, the pressure decreases. That means here the pressure will be less. So if the pressure at same point is less than saturation vapor pressure, the boiling will take place. After boiling, bubble will form. These bubbles were carried to high pressure region due to velocity of the flow. So when when the bubbles reach to high pressure zone, due to high pressure, these bubbles get collapses, and this process is known as cavitation. So due to cavitation, what will happen? The erosion of side walls, pitting of side walls, and wear and tear of walls will take place. So we don't want this cavitation process to occur. So for that, we have to maintain the absolute pressure at any point. The absolute pressure at any point should be greater than vapor pressure of the liquid. So if you maintain this pressure, there will be no cavitation occurrence. So to avoid Okay. So to avoid cavitation, the absolute pressure should be greater than absolute pressure should be greater than vapor pressure. Pressure of the fluid should always above vapor pressure, that is pressure of the liquid should be greater than vapor pressure. If the fluid is high volatile, for suppose let's take some methane or some kind of methane, it has high volatility. So its vapor pressure will be high, therefore chances of cavitation occurrence is more. Okay, if the fluid is more volatile, then there is a chances of cavitation occurrence is more because the vapor pressure is high. If you take mercury, it has least vapor pressure due to high cohesive bonding. Mercury has least vapor pressure. This is the reason why we use mercury in barometric, barometer we use mercury as a pressure measuring liquid. So why we use mercury? Because it has least vapor pressure. Okay, so cavitation in case of hydraulic turbines will occur at the outlet, and in case of centrifugal pumps cavitation will occur at inlet. Okay, what is the meaning of it? So cavitation, chances of cavitation occurrence will be at different locations. If you consider, first one is at the outlet of turbine. Second one is at the inlet of centrifugal pumps, or you can say at the inlet of pump. Third one is at the summit, or you can say at the top of the summit of the siphon. So these are the examples where cavitation chances occurs. So cavitation chances occurs in the sense at these locations the absolute pressure is, there is a chance of absolute pressure is minimum. That means there is a chance of absolute pressure falling below vapor pressure of the liquid. Why at the outlet of the turbine? If you say if you take turbine, after turbine is flowing, let's take after turbine is flowing, the water will fall freely. And if you take the pressure at this point is atmospheric pressure at this point, if you consider as the point is having more datum, so at this point there is a chances of pressure falling below atmospheric pressure. So at the outlet of the turbine and at the inlet of the pump, at the summit of the siphon, we have least pressure. So there is a chances of occurring cavitation process. So this is with respect to surface tension. So that is the decrease in surface energy is sigma into change in surface area. Okay, why? Because the surface energy is less, there will be more stability to the system. Okay, so thank you one and all. So this will cover the entire fluid properties. Okay, for AE and AW examinations, this information is more than sufficient for fluid properties. So I have explained all the important points. Okay, so I will cover remaining all topics also in the same manner. Of all the subjects I will cover. First I will complete fluid mechanics and strength of materials in 1 month or 2 months. So after that I will pick another subject. So please subscribe to my channel. If you have any suggestions you want to give, please comment below, and please like the video. Please subscribe to my channel. Thank you.